This is the $500 billion semiconductor industry powering the modern digital world.
Some of these machines cost hundreds of millions of dollars each.
Each wafer holds hundreds of powerful microchips smaller than a fingernail. From smartphones to AI servers, nearly every modern technology depends on these chips. Semiconductor factories operate worldwide to meet constantly rising global demand.
Modern transportation, healthcare, and artificial intelligence all rely on advanced microchips.
Cleanrooms are thousands of times cleaner than hospital operating rooms. It all begins with purified silicon extracted from common sand.
The Czochralski process forms ultra-pure single-crystal silicon ingots.
These ingots can weigh over 100 kilograms.
Diamond wire saws slice the ingot into ultra-thin wafers. Each wafer is polished to near-perfect atomic smoothness. Thin oxide layers form the foundation of transistor structures. Photoresist coating prepares the wafer for lithography patterning.
Advanced lithography projects complex circuit patterns at nanometer scale.
Developers remove exposed photoresist to reveal precise circuitry. Plasma etching carves transistor structures into silicon layers.
Ion implantation precisely modifies semiconductor conductivity.
Metrology tools inspect patterns for microscopic defects.
This process repeats dozens of times to build complex circuits.
Copper wiring connects billions of microscopic transistors.
Each chip is electrical tested before packaging.
Dicing separates the wafer into individual microchips.
Packaging protects delicate circuits from external damage.
Final testing ensures performance meets strict specifications.
Modern mega factories produce millions of chips every month.
These microchips power global data centers and artificial intelligence systems. But building and operating these mega factories costs billions of dollars.
A single megafab can consume as much electricity as a large city. Ultra-pure water is essential, used constantly to clean wafers between every critical step. Automated chemical delivery reduces contamination risk while keeping production safe and consistent. Robots move wafers inside sealed pods, protecting surfaces from even microscopic particles. Every load port docking must be perfect, because one misalignment can ruin an entire batch. Deposition tools lay down ultra-thin films that form the core layers of each transistor. Some layers are only a few atoms thick, built one controlled cycle at a time.
Wafers are cleaned repeatedly, because even a single speck can destroy microscopic circuitry.
Fin rinse drying removes chemicals and moisture, leaving a perfectly clean surface for the next step.
Chemical mechanical polishing flattens each layer, ensuring perfect alignment for advanced patterning.
CMP makes the wafer surface mirror flat, preparing it for the next lithography cycle.
Photoresist is applied again and again, because each layer needs its own exact circuit pattern.
Baking hardens the photoresist, stabilizing it before exposure to powerful lithography light. Alignment is critical because every new layer must match the previous one within nanometers.
In seconds, light patterns billions of features onto the resist, defining the next transistor structures. Developer chemicals reveal the pattern, turning invisible exposure into real microscopic geometry. Plasma etching removes material with extreme control, carving nanometer shapes into complex layers. Cluster tools move wafers between chambers without exposure, keeping conditions stable and contamination-free. Ion implantation tunes electrical behavior by embedding controlled atoms into silicon at precise depths. Annealing repairs crystal damage and activates dopants, locking in the wafer's electrical properties. Metrology checks critical dimensions, because tiny variations can reduce yield and performance.
High-speed inspection scans for defects early, preventing costly failures later in the process. Electron microscopes reveal structures smaller than light can see, confirming patterns are truly correct.
Conductive seed layers prepare the wafer for copper wiring that will connect every circuit block. Electroplating fills tiny trenches with copper, forming the interconnects that carry signals and power. After copper fill, CMP removes excess metal and restores a perfectly flat surface again. Layer by layer, the chip grows into a dense stack of devices and wiring. Robotic transport highways move wafers non-stop, linking hundreds of machines across the cleanroom. This is manufacturing on a microscopic scale, built using machines the size of buildings. Next, we follow the wafer into testing and packaging, where microchips become finished products. Before dicing, every die is electrically tested to measure performance and detect defects early.
Look at the thermal uniformity on wafer 7. That red zone is critical.
I see it. The sensor data confirms the anomaly during the last cycle.
Each wafer is mapped carefully, separating functional chips from defective regions.
After testing, wafers move to dicing, where individual microchips are separated precisely.
Diamond saws cut the wafer into hundreds of tiny chips without damaging circuitry.
Automated systems sort functional chips, maximizing usable output from each wafer.
Packaging protects delicate circuits and connects them to the outside world.
Gold wires form electrical connections thinner than a human hair.
Flip chip technology improves performance by shortening electrical pathways dramatically. Encapsulation shields the chip from heat, moisture, and mechanical stress. Laser marking ensures traceability across global supply chains. Each packaged chip undergoes final testing to verify speed and reliability. Burn-in chambers simulate years of operation in just a few hours. Optical inspection ensures flawless packaging before shipment. Taping systems organize thousands of chips for efficient global distribution. Moisture-controlled packaging prevents damage during transportation and storage.
Millions of chips leave this facility every month for customers worldwide. Global logistics networks distribute microchips across continents daily. Building a modern semiconductor fab can cost over $10 billion.
Most of the investment goes toward advanced machines and cleanroom infrastructure. Some lithography tools alone can exceed $200 million each.
Top fabs process millions of wafers every year at astonishing efficiency. Semiconductor revenue continues growing as digital demand accelerates worldwide. Artificial intelligence is driving unprecedented demand for high-performance chips. Electric vehicles now require thousands of chips for advanced functionality.
Defect density is spiking right here on the chart.
But the overall yield is stable. We should analyze the root cause before stopping the line.
Agreed.
These mega factories operate 24 hours a day, every single day.
Artificial intelligence now optimizes equipment performance in real time.
Look at the data from the microscope. The alignment is nearly perfect now.
I see it. The robotic arm performed the calibration.
Expansion projects aim to meet exploding global demand in the coming decade.
The wafer alignment seems off on Bay 3.
Yeah, the throughput dropped significantly after the last cycle.
Now let's talk business. How much chips cost to make, and how mega factories earn billions. Most fab spending goes into equipment. Hundreds of tools working non-stop inside ultra-clean environments. Cleanroom infrastructure is expensive. Air filtration, vibration control, and strict environmental stability cost a fortune. Fabs spend heavily on ultra-pure water and chemicals because every wafer requires repeated cleaning and processing. Downtime is extremely costly. Every minute offline can translate into massive lost production and revenue. Mega fabs measure success by throughput. How many wafers move through the line every single day?
Yield is everything. Higher yield means more sellable chips from the same wafer cost.
Even a 1% yield improvement can add millions of dollars in value across production. Large fabs run massive wafer start volumes annually, turning raw silicon into finished chips at scale.
Smaller process nodes require more steps, tighter control, and more expensive tools, driving costs upward.
A single advanced chip can require hundreds of steps, repeated layer after layer with extreme precision.
Specialty gases are critical and costly, enabling deposition, etching, and plasma processing across the fab. Robots repeat actions perfectly, improving consistency and protecting yield across millions of chips. AI and cloud computing drive high-margin demand for advanced chips with extreme performance requirements. Smartphones still ship in huge volumes, requiring efficient, reliable chip production at scale. Automotive electronics require robust chips, tested for reliability in heat, vibration, and long lifetimes. Chip pricing varies by complexity. Specialized high-performance products command far higher revenue per unit.
This spike in the forecast needs verification.
I'm cross-referencing the order volume now. It seems we have a major uptick in Sector 7.
Let's adjust the production schedule.
The global semiconductor market is enormous, driven by constant upgrades in computing, connectivity, and automation. When output reaches millions of units per month, small efficiency gains translate into huge profits. Testing costs money, but it protects customers by ensuring only reliable chips ship worldwide.
Zoom in on Sector 4. That cluster looks anomalous.
Confirmed. Tagging for immediate rework.
The profit engine is utilization, keeping expensive tools running non-stop with stable, high-yield production. Finished chips move through secure logistics systems, tracked carefully from fab to customer delivery.
Global shipping moves these chips quickly, feeding electronics factories around the world every day.
In semiconductors, profitability comes from yield, speed, and keeping billion-dollar equipment running efficiently.
Next, we look at the future: AI automation, advanced packaging, and the next wave of mega factory upgrades.
AI is transforming fabs by predicting failures early and optimizing processes faster than humans ever could.
Predictive systems analyze sensor data constantly, preventing breakdowns before they disrupt expensive production.
Digital twins simulate the entire factory virtually, allowing engineers to test improvements safely. Researchers push towards smaller nodes, packing even more transistors into tiny spaces.
New transistor designs promise greater efficiency and performance at lower power consumption.
Chiplet architecture allows multiple specialized dies to work together as one powerful processor.
Three-dimensional stacking increases performance by reducing signal distance dramatically.
High-bandwidth memory enables AI processors to handle massive data workloads efficiently.
Future lithography systems aim for even finer resolution and greater throughput.
Sustainability efforts focus on reducing energy use and recycling water efficiently.
Modern fabs pursue aggressive environmental targets while maintaining high production output. Expansion projects are underway globally to meet explosive semiconductor demand. Public incentives often support large-scale investments in domestic semiconductor manufacturing.
The visualization highlights the critical path right here.
I see it. The new algorithm handled the placement constraints perfectly.
Fully automated fabs operate with minimal human intervention, maximizing consistency and safety.
Thousands of sensors monitor temperature, vibration, and chemistry in real time.
Machine learning models continuously refine process parameters to boost overall yield.
Beyond silicon, quantum research explores entirely new computing possibilities.
Edge computing increases chip demand across smart cities and connected devices.
Expanding data centers require ever more advanced and efficient processors.
Industry forecasts predict continued growth throughout the coming decade.
Self-calibrating tools reduce errors and maintain peak performance automatically.
The stress test results on the new model look promising.
I agree, but we need to verify the thermal load data from Sector 9.
I'm running this.
Innovation moves rapidly from laboratory research into billion-dollar production facilities. From sand to silicon, this industry powers nearly every modern technology. It combines extreme precision, massive machines, and staggering financial investment.
The next generation of chips will drive artificial intelligence and global connectivity.
Mega factories like this operate non-stop, shaping the digital future.
This is how microchips are made inside the $500 billion semiconductor industry. Subscribe for more deep dives into the world's most advanced mega factories.
Future cleanrooms will become even more automated and energy efficient.